Hello and welcome to this video on eigenvalues, eigenspaces, eigenbases, and the algebraic and geometric multiplicity of an eigenvalue. So lots of eigen stuff in this video, but they're all very closely related, as you'll see. So in this video I'm going to define something I've defined in previous videos, the eigenspace for a particular eigenvalue corresponding to a particular eigenvalue of a matrix. And I didn't call it an eigenbasis, but any basis for an eigenspace is an eigenbasis. I'll get to that. And then some new words that you haven't seen in previous videos. What is the algebraic multiplicity of an eigenvalue, and what is the geometric multiplicity of an eigenvalue? Okay. So first, about eigenspaces. So suppose we're looking at an n by n, right, a square matrix A. Also suppose that we have found at least one eigenvalue called lambda. Right, so suppose lambda is an eigenvalue of matrix A. The eigenspace of A corresponding to this lambda is the set of all the solutions, right, which are vectors x, all the solutions to this equation A minus lambda I times x equals the zero vector. In other words, the eigenspace of A corresponding to lambda, which is now going to be, I hadn't written this in previous videos, but now we're going to be introducing the eigenspace of A corresponding to a given eigenvalue lambda will be denoted by this E with a subscript of lambda, and then in parentheses afterwards the matrix A. So that's the eigenspace of A corresponding to lambda. This will be just the null space of the matrix A minus lambda I. Right, because again, I'll remember the null space of a matrix was all the vectors you could multiply by that matrix and get the zero vector. That's exactly what we're doing. Now in some texts, I've seen the eigenspace corresponding to a particular eigenvalue being just the eigenvectors and not the zero vector. But then they mention in certain texts that, if you take this set of eigenvectors and throw the zero vector in there, you get a vector space, right? A subspace of Rn, right? If it's an n by n matrix. So I'm just going to have the eigens. In most texts I've seen, the eigenspace contains all of the eigenvectors and the zero vector, right? So that'll make it a vector space. I mean, the word space is in eigenspace, so I'm not going to use the word space lightly. If I say something is an eigenspace, I would like that to be a vector space right away. So that's what I've written here. Okay, so the eigenspace of A corresponding to lambda contains all of the eigenvectors of A corresponding to lambda and the zero vector. Right? And remember, the zero vector is not an eigenvector, but having the zero vector in this set makes it a vector space. Again, because it is we've seen the null space of a matrix is a vector space, right? So, and zero is a solution to this equation right here. The zero vector would be a solution. Okay, so the eigenspace of A, the way I'm defining it, corresponding to lambda, contains all the eigenvectors of A corresponding to lambda, and the zero vector is also in there. Right? But just be careful. Remember that the zero vector, by definition, is not an eigenvector. Eigenvectors are non-zero. And as I said earlier, the eigenspace of A corresponding to lambda is a vector space, and in fact is also, it's going to be a subset of Rn, if A is an n by n matrix. So this is a subspace of Rn, right? Meaning it's not empty, right? Because I mean the zero vector's in there, and if matrix A should have at least one, eigenvalue, which will have a non-zero eigenvector associated with it. So it's non-empty. It's closed under addition, right? If you take two eigenvectors, add them together, you get another eigenvector corresponding to lambda. And it's also closed under scalar multiplication. If you were to take an eigenvector corresponding to lambda, multiply it by a scalar, that scalar multiple would also be an eigenvector corresponding to lambda. So, and then all the other, 8 vector space axioms would be satisfied because, all these vectors in this eigenspace are also vectors in Rn, right? So again, you can double check that on your own, that it's closed under vector addition, closed under scalar multiplication, and non-empty. Alright, so these next couple pages have to do with some more definitions, and then we'll get into some examples where I bring these definitions back, or I bring the words back. So, since the eigenspace of A corresponding to lambda is a vector space, it should have a basis, right? Well, eigenbases here. An eigenbasis is just any basis for the eigenspace of A with corresponding to lambda. Right, and the way that these are found is by, we've done this, but I've done this before. I've done this in previous videos. Again, if you've been watching and following, you've seen me state the eigenspaces of certain eigenvalues, of certain values of lambda, by finding the solutions to this equation, right? This A minus lambda I, where I is the identity matrix, times x equals the zero vector. Then some other words that I didn't bring up in previous videos, but you could easily figure out what they are based on trying to find solutions to this equation, and also to solutions of the characteristic equation for a matrix. So our final definitions here are the algebraic multiplicity of an eigenvalue and the geometric multiplicity of an eigenvalue. All right, now the algebraic multiplicity is kind of like, if you go back to algebra class or pre-calculus, you probably discussed at some point the multiplicity of a zero of a polynomial, the multiplicity of a root of a polynomial, and that was just the number of times that zero repeated as a solution, or repeated as a zero or a root of that polynomial. So the same concept here for algebraic multiplicity. The algebraic multiplicity of an eigenvalue lambda is the number of times the eigenvalue repeats as a solution of the characteristic equation for that matrix. And I wrote down what the characteristic equation for a particular matrix A is, and a value lambda. It's the determinant of A minus lambda I. When is that determinant equal to the number 0? And you find out how many times is a particular value lambda a solution. Is it just repeating once, twice, 3 times? And you'll see that the power or the exponent on the factor that that particular eigenvalue makes equal 0 will be the multiplicity, or the algebraic multiplicity. And you'll see examples of that coming up. All right, then the other one is the other kind of multiplicity of an eigenvalue is the geometric multiplicity. the geometric multiplicity of an eigenvalue, lambda, is the dimension of the corresponding eigenspace, right? The eigenspace of A that corresponds to lambda, right? Remember, this is a vector space, and it'll have an eigenbasis, and the dimension of that vector space is simply how many vectors are in an eigenbasis, right? A basis for that vector space. And one thing you're going to notice, and a lot of I'm not going to go over the proof of this. That's not the point of this video, but one result that can be shown, and if you'd like to find, most texts I've seen have a proof of this outline when they mention it, is the following. The geometric multiplicity of an eigenvalue lambda will be either less than or equal to the algebraic multiplicity of that same lambda. Okay, so the dimension of the eigenspace corresponding to lambda will be less than or equal to the number of times lambda repeats as a solution in the characteristic equation. Right, geometric multiplicity less than or equal to the algebraic multiplicity. And again, I'll write all this out when we go through some examples. All right, so lots of definitions, lots of words there, fancy words, describing pretty simple concepts. But now let's get into some examples where I'm given a square matrix, so called A, and I'll find first the eigenvalues, right? So you've seen me do this before in previous videos, so this is just a nice refresher. But now I have these new words, eigenbasis and algebraic multiplicity and geometric multiplicity. All right. So here's a 2 by 2 matrix with columns 2, 1, negative 12, negative 5. And first, I'm going to find the spectrum of A. Remember, that was this lambda of A. Remember, this is just the set of all the eigenvalues. So just find all the eigenvalues. And while I'm finding these eigenvalues, we'll come across the algebraic multiplicity of the eigenvalues for this matrix. All right, so if I'm trying to find the eigenvalues of a matrix A, we're going to be solving what's called the characteristic equation. Right? When is the determinant of A minus lambda I, where I is that this case a 2 by 2 identity matrix, when is that equal to 0? All right, so I'll start with the left side here. We're finding a determinant. Now this is going to end up being, this left side is called the characteristic polynomial. Right, you're going to end up with a polynomial over here that is dependent on lambda. Right, that'll have a polynomial in lambda. So I'll have determinant, right, this straight little bar there. And then what is the matrix A minus lambda I? All right, A minus lambda I is simply A where you're subtracting lambda down the main diagonal entries. So first row, first column, 2 minus lambda. Second row, second column, negative 5 minus lambda. And then the other positions, not on the main diagonal, stay the same. Negative 12 and 1. All right, now this is a simple 2 by 2 matrix determinant here. So I'm going to take like this cross product here minus this cross product here. So it's 2 minus lambda multiplied by negative 5 minus lambda minus and then negative 12 times 1. All right. In multiplying these two, I'd get a quadratic polynomial here in lambda. All right, you see I'd have a well, I'll do the last first. Negative lambda times negative lambda would be positive lambda squared. Then the inners and outers, you have positive 5 lambda minus 2 lambda. That'd be positive 3 lambda when you put those together. And then the firsts, 2 times negative 5 is negative 10. But then I have plus 12. So negative 10 plus 12, right, minus negative 12. That'd be positive 2. And this is called, again, the characteristic polynomial. And my question is, for what values of lambda is this equal to 0? Now I would recommend, if you are able to, factoring the characteristic polynomial completely, over the integers, like you normally would in any algebra class you were taught. So this is actually factorable. Now, if it weren't factorable, then I could use, when I set it equal to 0, I could use the quadratic formula or something, completing the square. But this is nice and factorable. This factors to lambda plus 1 times lambda plus 2. And the big question again is, when is this equal to 0? Well, it's equal to 0 when I have a product equal to 0. The only time a product is equal to 0 is when one of the factors is 0. So when is lambda plus 1 equal to 0? Well, that would be equal to 0 when lambda was negative 1. Or, when lambda plus 2 is 0, the whole thing will be true, right? So that happens when lambda equals negative 2. All right, so there you go. Right, here are all the solutions of this characteristic equation. And now we have, the spectrum. Right, so the spectrum of this matrix A is, again, just a set with the eigenvalues in it, negative 2 and negative 1, or negative 1 and negative 2, whatever order you want. Now, when you solve the characteristic equation like this, you can then easily state the algebraic multiplicity of each eigenvalue. If you look at the factors, look at for lambda equals negative 1, ask yourself, how many factors of the characteristic polynomial does this make equal 0? Well, only lambda plus 1. And notice it's lambda plus 1 to the first power. Right? There's only one factor that negative 1, when plugged in for lambda, would make equal 0. So we're seeing here that the algebraic multiplicity, right, so getting to some of those other words that we came across. So one thing to note is that the algebraic multiplicity of lambda equals negative 1 is 1, right, because there's only one factor of the characteristic polynomial that makes 0. Or it's a solution that doesn't repeat more than once. Right? It only repeats, one time, I guess it comes up one time. All right, so 1 is the algebraic multiplicity of lambda equals negative 1. And the same thing for the other eigenvalue, lambda equals negative 2. Ask yourself the question, how many factors in the characteristic polynomial does negative 2 make equal 0? Well, if I plug in negative 2 here, that wouldn't be 0, but here it would. And this is only, again, this is only lambda plus 2 to the first power, right? And the exponents on factors will help you determine pretty easily what the algebraic multiplicity of a particular eigenvalue is. So I'm seeing that negative 2 is only a solution to this equation once, right? It only makes one factor equal 0. So yet again, the algebraic multiplicity, I'll write it again, so hopefully we get used to it. The algebraic multiplicity of lambda equals negative 2 is also 1. All right, is also 1. Because the number negative 2 only appears as a solution to this equation one time. Okay. Great. So now after finding the eigenvalues and their corresponding algebraic multiplicities, next I can go into finding the eigenvectors that correspond to these two eigenvalues and then their eigenspaces. Because remember, the eigenspaces are just the eigenvectors with the zero vector, right? So just every solution to a minus lambda I times x equals 0. Right, so that's part 2. So we have negative 2 and negative 1 as eigenvalues. And then part 2, I'm going to find the eigenvectors and eigenspaces corresponding to these eigenvalues. Really just, I'm going to focus mostly on the eigenspaces, because again, if you know the eigenvectors, right, again, just add the zero vector in that set, and then you've got the eigenspace. So find the eigenspaces corresponding to each eigenvalue. So I'm going to start off with, let's go with lambda equals negative 1. All right, how about that? All right, so for lambda equals negative 1. Now remember, to find the eigenvectors, or just the eigenspaces of a particular eigenvalue, you are finding the solutions to this equation, a minus lambda I times x, when is that equal to the zero vector? All right, now you know what lambda is, right? Well, the unknowns here, what you're trying to find are these vectors, these x's, that make this true. And the set of all the solutions to this make up what's called the eigenspace corresponding to negative 1 here. All right, so if I replace lambda with negative 1, we're looking at the equation a plus I, right, minus negative 1 or plus 1I times vector x equals the 0 vector. All right, now matrix A is up here, right? Matrix A is up here. Now, what would A plus I look like? Let me just fold this up a bit. All right, what would the matrix A plus I look like? Well, that's just simply adding 1 to the main diagonal, right? The main diagonal entries. So this is the matrix, 2 plus 1, 3, negative 5 plus 1, negative 4 for the main diagonal entries, and then the other two stay the same, negative 12 and 1. Multiplied by, now this is a 2 by 2 matrix, okay, so the vector x is going to have, two components, say x1 and x2. And I would like this to, I want to know when this is equal to the 0 vector, and it would be the 2 by 1, 0 vector, the 0 vector from R2. Alright, so I'm not going to write the augmented matrix for this, where you have this matrix here and then a bar and then the zeros, because when you have that column of zeros, it's going to stay a column of zeros, whatever row operations you perform. So I'm going to take the matrix A plus I and put it into a reduced row echelon form. Now you can use a calculator for this, but this is only a couple of rows, and it's pretty easy to see, I think. If I take -3 times row 2 and add it to row 1, that'll make row 1 a bunch of zeros, and then I switch rows, and we get this here, 1, -4, 0, 0. And again, imagine, right, these are the coefficients of x1, coefficients of x2, and then you have equals 0 and 0, right? So the second row tells me that 0 is equal to 0, which is fine, right, which is totally fine. And then let's go and state the solutions here. So look for your pivots, right? Where are those leading ones in the rows of row echelon form here, reduced row echelon form? So this first column, the column that corresponds to, that has coefficients of x1, is a pivot column. So x1 is going to be what's called a basic variable. Then the second column, right, is not a pivot column. So x2 is going to be a free variable, right? Meaning I can replace x2 with any value I wish, any real number I want. And I personally like doing this, right? I like you can leave it as x2 if you wish. I like to replace my free variables with other expressions, right? Other parameters that can take on any real number value. Usually it's t, right? Where t is any real number. And then from that first row, right, again, the second row isn't important. This is 0 equals 0. The first row tells me that, 1x1 minus 4x2. So minus 4t, right? I call it x2t. And again, you got the equals 0 on the other side, right? Equals 0. So the value of x1 must be 4 times t. And then putting these together, we can state the solutions to my equation, this a plus I times x equals 0. And once I have the solutions to this equation, I then have the eigenspace for lambda equals -1. Right. So the solutions, every x I use, right, every vector x I can replace with here, it's going to have two components. The first component, x1, is 4 times this choice of t. The second component, x2, is just the choice of t. And both of these have t in common. Pull t out, times the vector 4, 1. So there, right? All the solutions of this equation are scalar multiples of the vector 4, 1. Even the 0 vector. Now I know the 0 vector isn't an eigenvector, but it is a solution to this equation. So it's going to belong to the eigenspace, right? Space is in there. It should be a vector space, should have the 0 vector in it. So the eigenspace, right, the eigenspace of matrix A corresponding to lambda equals -1. Now instead of writing all that, remember this is the notation for this. This is the eigenspace of A corresponding to lambda -1. Right? So again, that's where the lambda goes, right? -1 down here. Well, you could say it's all these vectors, write the description like this, but remember the set of all vectors that are scalar multiples of 4, 1 is simply the span of that set with the vector 4, 1 in it. Okay, there we go. Or again, you could write out the little scalar multiples such that t is a real number. Right? So remember, this has all the eigenvectors of A corresponding to -1. Right? Also, it has the 0 vector. Right? It is a vector space. And it is also, a subspace of R2. Right? Now, once you've found an eigenspace in the fashion that we have, by solving this equation up here, putting your equation, the matrix into reduced echelon form or just echelon form, solving that way. You should have come up with also an eigenbasis. Right. This set with the vector 4, 1 in it is clearly a basis for this eigenspace, right? Every vector in the eigenspace is a scalar multiple of 4, 1, and a set with a single non-zero vector is definitely linearly independent. So this set spans the space and is linearly independent. Therefore, it is a basis. So again, I'll just write eigenbasis now. For this first example, I'll write eigenbasis, corresponding to lambda equals -1. But I'll just write eigenbasis in the future. But now we have this as well. And now that we have an eigenbasis for the eigenspace, we can state the dimension of the eigenspace. Right? The dimension of that eigenspace of A corresponding to lambda equals -1 is just 1. Right? There's only one vector in a basis, one non-zero vector, right, in the basis for this space. And oh wait, remember this had a fancy name. The dimension of the eigenspace corresponding to an eigenvalue was called the geometric multiplicity of that eigenvalue. Right, so we had algebraic multiplicity earlier. Right, but again, the geometric multiplicity of lambda equals -1 is just the dimension of that eigenspace corresponding to -1. So we're seeing here that the geometric multiplicity of -1 is 1. Earlier, we saw the algebraic multiplicity of -1 was also 1. And as I said, that should happen. They're not always going to be equal, but remember this statement earlier. The geometric multiplicity of an eigenvalue should be either less than or equal to the algebraic multiplicity. And we are seeing that happen here. 1 is less than or equal to, right? It's actually equal to 1. Right? The geometric multiplicity will be less than or equal to the algebraic multiplicity. All right. So that was for -1. Let's do the same thing for -2. All right. So for lambda equals -2, so here's matrix A again, way back up here. So again, I'm going to find, now I know, the algebraic multiplicity is 1. Now I'm going to find the eigenbasis, the eigenspace of A corresponding to -2. Then we'll state an eigenbasis. And once we know the dimension, right, once we know an eigenbasis, we'll know the dimension of the eigenspace and therefore the geometric multiplicity. All right. So remember, in order to find eigenvectors and the eigenspace corresponding to a particular eigenvalue, you are solving this equation A, minus lambda I. So minus negative 2i, so that'd be a plus 2i in this case, times some vector x equals the 0 vector. When is that happening? The matrix a plus 2i. You're just adding 2 to the main diagonal entries of a, right? So 2 plus 2, 4. Negative 5 plus 2, negative 3. And then the other two stay the same, negative 12, positive 1. All right. Then times again, this is a 2 by 2 matrix, so the vectors we're looking for will have two components, say x1 and x2. And I want this to be equal to the 0 vector from R2. All right. As before, put this matrix here into a reduced row echelon form, which is pretty straightforward. Again, this time it's only a 2 by 2. Can you see if I multiply the second row by negative 4 and add it to the first row would be full of zeros, 2 zeros, and then I just switch the rows. So 1, negative 3 comes up top, and then 0, 0 down here, and there. This is in reduced echelon form. And don't forget, you're imagining the equals 0 on the other side. Right, so yet again, my pivot is in the first column, so x1 is basic. The second column does not have one of those leading ones or a pivot. So x2 is my free variable. And I'm going to replace that free variable with t again. So x2 equals t, and then from the first line, pardon me, we have x1 minus 3t, right, 3x2, equals 0. So x1 would have to be equal to 3t, right? I would add 3t to both sides. So the solutions of this equation, this a plus 2i times x equals 0, are these vectors. I can replace x with, again, a vector with two components, and the first component is going to be 3 times whatever I choose for t. The second component is whatever I choose for t, and pulling the t out of those, get t times the vector 3, 1. All right, and there we have described every vector that's in the eigenspace of A corresponding to lambda equals negative 2. Every multiple, every scalar multiple of the vector 3, 1 is a solution to this equation, including the 0 vector, right? Now I know the 0 vector isn't an eigenvector, but all the other ones are, right? All the other non-zero solutions are eigenvectors corresponding to negative 2. All right, so the eigenspace of A corresponding to lambda equals negative 2, right, that's what this symbol means here, is just, all the scalar multiples of the vector 3, 1. That's the span of the set with the vector 3, 1. Okay, so there's the eigenspace. And again, if you've done this correctly, you can very easily see a basis for that space, right? The eigenbasis. So this has eigenbasis. Which is, just that set with the vector 3, 1 in it, right? It clearly spans the space, right? Every vector in this eigenspace is a multiple, a scalar multiple, linear combination, however you want to put it, of the vector 3, 1. And it's only a set with a single non-zero vector, so it's definitely linearly independent. So here is another eigenbasis for A, this time corresponding to lambda equals -2. And then we're very now easily seeing that the dimension, right, the dimension, and I'll use the shorthand notation dim, the dimension of this eigenspace, right, the eigenspace of A corresponding to -2 is 1 again. Right? There's only one vector in a basis for it. And remember, this dimension of the eigenspace is called the geometric multiplicity. Of lambda equals -2. Great. And as I mentioned before, the geometric multiplicity of an eigenvalue should be less than or equal to the algebraic multiplicity. And we saw earlier the algebraic multiplicity of -2 was also 1. So again, they are equal, but the geometric will be less than or equal to the algebraic. All right, so that's it for that example. Wow, right? It takes a bit even for just a 2 by 2. But you see what happened there, right? First I found all the eigenvalues. I found the spectrum of the matrix by solving the characteristic equation. Once that characteristic equation is solved, you can very then easily state the algebraic multiplicities of the eigenvalues. Right? How many times do they repeat as solutions of the characteristic equation? Once you've got that down, then you take and try to find the eigenvalues and basically the eigenspaces of the eigenvalues separately. And once you've found the eigenspaces, you can state a basis pretty easily, hopefully, if you've done the solving correctly. And once you've stated a basis, then you can very easily state the dimension, right, which will be that geometric multiplicity. All right, so it all comes together. All right, next example. I've only got 3 of them. This will still run long. Now this one's not so bad. I have A equals this 3 by 3 matrix. 2, 0, 0, 1, 2, 0, 0, 0, 2 are the columns. Now you might notice, remember how if you take a square, if I draw a little dotted line here down the main diagonal, right, you have an upper triangle and a lower triangle of the matrix. You see how all the values in the lower triangle are zeros? Means this thing is an upper triangle. The only non-zero entries are either on the main diagonal or on the upper triangle. So this is one of those upper triangular matrices. And if you recall, the eigenvalues of a triangular matrix, whether it be upper triangular, lower triangular, or diagonal, were just the diagonal entries. So that first part, when I'm trying to find the spectrum of A, well, the spectrum of A I can tell you right away because it's triangular. The eigenvalues of this matrix will be 2, and that's it. But you notice how it's 2 3 times, but the only eigenvalue is 2. Right? So the spectrum would contain only the number 2. It's just 2 is repeated. Now, if I want to state the algebraic multiplicity of 2, and you probably can guess that it is 3 because I'm seeing 3 2's here. But let's actually write out that characteristic equation again. So where I'm trying to solve this equation, right? The determinant of A minus lambda I, when is that equal to 0? All right, now this determinant of a minus lambda I, that would be again a big bar here. Just subtract lambda from the diagonal entries. Right? So we have 2 minus lambda in the first row, first column, 2 minus lambda in the second row, second column, 2 minus lambda in the third row, third column, and then all the other entries stay the same. So zeros in the lower triangle, and 1, 0, 0 here, 1, 0, 0 in the upper triangle. Now, this is still upper triangular. All right, this is still an upper triangular matrix, right? You see, again, draw a little segment here, imagine a little line going through the main diagonal, and that lower triangle is full of zeros. So this is, upper triangular. Now remember, if both were full of zeros, the upper triangle and lower triangle, then it's called diagonal. But either way, whether it's upper triangular, lower triangular, or diagonal, the determinant, right, remember very simply, you can do cofactor expansion and stuff, but hopefully you remember this result. The determinant of a triangular matrix was simply the product of the diagonals, the diagonal entries. So this is 2 minus lambda cubed. Do you see that? 2 minus lambda times 2 minus lambda times 2 minus lambda. And so, and the question is, when is this equal to 0? And that happens when lambda is equal to 2 only, right? When 2 minus lambda equals 0. Right. So the spectrum of A is just, the set with the number 2 in it. That's the only eigenvalue. And then, as I said in the last example, now that I have this characteristic equation written out, we can very now easily, clearly see the algebraic multiplicity of the number 2. Right? Ask yourself, how many times is 2 a solution to this? How many factors of the characteristic polynomial does this 2 make equal 0 when I replace lambda with it? Well, you see 2 minus lambda here, it makes this factor 0, and notice that this means this power of 3, right? That means that there are 3 of those factors. There's 2 minus lambda, 2 minus lambda, and 2 minus lambda again. So this is a repeated solution, 3 times. So the way that what we would say then is that the algebraic multiplicity of lambda equals 2 is 3. Right? 3. Again, that exponent, or again, just count the number of factors of the characteristic polynomial that particular eigenvalue would make 0. Okay, wonderful. So I found all the eigenvalues, just 2, the number 2. I have stated the algebraic multiplicity of this eigenvalue, which is 3. And now we can move on. All right, now let's find the eigenspace of A corresponding to this eigenvalue. So next I'm going to, 2, I'm going to find that eigenspace of A corresponding to 2, right? The only eigenvalue was 2. Okay, so remember how to do this. This is finding all the solutions of this equation. A minus lambda x. All right, well, lambda's 2 here. So A minus lambda I. And lambda's 2. So A minus 2I times some vectors x, right? When is that equal to the 0 vector? And I have A up there. Right, what does A minus 2I look like? Well, if I take A minus 2I is just subtract 2 from the main diagonal entries of A. 2 minus 2, 2 minus 2, 2 minus, so all the main, all those become 0. And then, every other entry remains the same. 0, 0, 0 there, 1, 0, and 0 there. And then the vector x, right, would have to have 3 components. This is a 3 by 3 matrix now, so say x1, x2, and x3. And this, I want this to be equal to the 3 by 1 0 vector, right? The vector from R, the 0 vector from R3. Then as before, I take this matrix, this A minus 2I, and put it into reduced row echelon form, which it already is. This is already in reduced row echelon form. Right. So let's look at it, find our pivots. The first row has a pivot, right? This first non-zero entry is a 1. That's down the second column, so x2 is a basic variable. Right? But then the first column and third column don't have one of these pivots, right? So x1 and x3, right? Both x1 and x3 are free. I can let both of them be whatever I want. So since there are 2 of them, I need 2 different expressions. I'm going to say replace x1, say with the letter s, where s is any real number. And I'm going to have x3 be t, where t is any real number. Just make sure they're different expressions, because they are different variables. Alright, well then what we're seeing here, the only row without a bunch of zeros is the first row, and I'm seeing that x2 plus no x1 plus no x3, just x2 has to be equal to 0. Right? From that first row there, we're seeing that x2 is always going to be equal to 0 for any solution to this equation. Alright, so putting all this together, the solutions of this equation, this a minus lambda I, a minus 2i times x equals 0, I can replace the vector x with some vector with 3 components, right? x1, x2, x3, where x1 is some number s I choose, x2 is always 0, and x3 is the number t that I choose. So 2, 0, 5, negative 8, 0, 100, 5, 0, 1, whatever. I choose something for s, something for t, and the second component is always 0. You have a solution. Now, I'm going to do something that you've probably seen me do in previous videos. There are 2 free variables here, 2 parameters, s and t. I'm going to split this up. I'm going to write this as a sum of a vector, one of 2 vectors, one involving the free variable s, right? So you have s in the first component, no s in the second component, no s in the third component. So s 0, 0. Plus, and then another vector involving just the other free variable t. There's no t in the first component, no t in the second component, and then 1 t, just t in the third component. And you see how this sum, the sum of these 2 vectors, would be this vector here. And then pulling these free variables out, I can pull s out of the first one. I'd have s times the vector 1, 0, 0. And then pulling a t out of the second one, plus t times the vector 0, 0, 1. All right, and what we're seeing is that all of the solutions to this equation, right, all the vectors that belong to the null space of a minus 2i, or the eigenspace of a corresponding to 2, however you want to say that, all the solutions are linear combinations of the vectors 1, 0, 0 and 0, 0, 1. Right? This is a linear combination of 1, 0, 0 and 0, 0, 1. So there, I have my eigenspace now. So the eigenspace of a corresponding to 2, right, that only eigenvalue 2, is the set of all linear combinations. Now you could write this out and just say as long as s and t are real numbers, or say it's the span of the set with the vectors 1, 0, 0 and 0, 0, 1 in it. Right, that's what the span means. It's the set of all linear combinations of these 2 vectors. Now again, this set does include the 0 vector, right? So I mean, I know the 0 vector is not an eigenvector, but any non-zero vector in here is an eigenvector corresponding to 2. Right. And if you did this correctly, which I know I did, this set here with these two vectors, 1, 0, 0, 0, 0, 1, form a basis for this eigenspace. Right, clearly they span the space, and they're, these two vectors are not scalar multiples of each other. Remember a set of vectors. Pardon me, the dog's barking. I'm sorry. And my apologies, but remember, any set with two non-zero vectors that aren't scalar multiples of each other are linearly independent. So we have an eigenbasis, right? Corresponding to lambda equals 2, which would just be this set with the vectors 1, 0, 0 and the vector 0, 0, 1 in it. Cool, alright. And now that I have this eigenbasis stated, I very easily now see the geometric multiplicity of this eigenvalue of 2, and that's 2, right? The dimension of this eigenspace, right? The dimension of the eigenspace that we're looking at there corresponding to 2 is 2. Right? There are two vectors in a basis for it. And remember, this dimension of the eigenspace is called the geometric multiplicity. Of lambda equals 2, right, of that particular eigenvalue. And let's test that statement I said earlier. Remember, the geometric multiplicity should be less than or equal to the algebraic multiplicity. And we saw on an earlier page that the algebraic multiplicity of 2, lambda equals 2, was 3, right? But the geometric multiplicity of lambda equals 2 is 2. But that still holds, right? The geometric multiplicity is still less than or equal, but this case this time it's less than the algebraic multiplicity of the same eigenvalue. So working out. All right. Great. All right, and then I have one last example where I have another 3 by 3 matrix. And I'm going to go through and find the spectrum, right? Find the eigenvalues. And then once you've found the eigenvalues, you could, pretty easily state the algebraic multiplicity. Then we're going to find the eigenspaces of those eigenvalues. And once you have an eigenspace, you should be able to state an eigenbasis. And once you have the eigenbasis, you should be able to state the geometric multiplicity, all pretty easily following that. Okay, so part 1 again. I'm going to find the spectrum of matrix A. All right, find all the eigenvalues. All right, so this is where I'm solving that characteristic equation for lambda, right? When is the determinant of A minus lambda I, when is that equal to 0? All right. So this one will be a little hairier, but that was the whole reason for it. I haven't seen too many, I haven't given you too many 3 by 3s in the recent videos that were very difficult to find determinants for. So I thought I'd throw at least one out there that was a little more involved. So bar for determinant, right? And then A minus lambda I, just subtract lambda from the diagonal entries of A. So 1 minus lambda for first row, first column, 5 minus lambda for second row, second column, negative 3 minus lambda for the third row, third column. And all the other entries stay the same. Okay. Alright, so this time I'm going to do some cofactor expansion. I'm just going to go across the first row. So I have 1 minus lambda multiplied by the minor, of the 2 by 2, the determinant of the 2 by 2 matrix, 5 minus lambda, negative 2, 6, and then negative 3 minus lambda. Alright, and this is, again, that's the matrix I get when I get rid of that row and that column with 1 minus lambda in it. Then plus 2 times the cofactor of that position. Remember the cofactor of an odd position, right? This is first row, second column, 1 plus 2 is 3, that's odd. The cofactor of an odd position was always the opposite of the minor. So instead of 2, I'm going to put minus 2, and then times the minor. So get rid of that row, that column. I have the matrix with negative 2 as the first row, negative 6, and negative 3 minus lambda. And then plus negative 2 times its cofactor. So again, minus 2. And the cofactor of an even position, that's first row, third column, 1 plus 3 is 4, that's even. The cofactor of an even position is just the minor, so just the determinant of the 2 by 2, getting rid of that column in that row. Negative 2, 5 minus lambda, negative 6, and 6. Okay. So this first one, you got 1 minus lambda multiplied by, and then all these are 2 by 2s here. So we got 5 minus lambda times negative 3 minus lambda, and then plus 12, right? Minus negative 12 plus 12. Alright, then we have minus 2 times in the bracket here, and here's this determinant. Alright. So negative 2 times negative 3 minus lambda, minus 12, and then we have minus 2 times, and then bracket, and then this determinant, negative 12, then minus, negative 6 times 5 minus lambda, so plus 6 times 5 minus lambda. Alright, and I'll simplify all this on the next page. So I have here, again, starting here, 1 minus lambda times, and multiplying this out, I get lambda squared, then plus 3 lambda minus 5 lambda, so that'd be minus 2 lambda. And then you have minus 15, but then the plus 12 at the edge of the bracket here, right before you leave the bracket. So minus 15 plus 12, that's minus 3. Alright, then here we have minus 2 times, and then if I simplify what's in here, I'll have 6. Well, let me do the lambda first, put things in highest power to lowest power order, descending order. Negative 2 times negative lambda will be positive 2 lambda. And then you have plus 6 minus 12, that'll be minus 6. Alright. And then finally I have another minus 2, right, minus 2 there, times, and then simplifying what's in the bracket here. Got negative 6, looking at the lambda first, 6 times negative lambda is negative 6 lambda. And then here I have plus 30, but then minus 12, so it's plus 18. Alright, now, you could multiply this out, get some cubic polynomial, multiply this out, nothing wrong with that. I am just seeing something here that I see how I can factor each term, right? This is one term, this is another term, there are 3 terms. Remember, every term is a product, 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 that you could separate with plus signs. I'm seeing how we can get a common factor in every term. Just follow me here. Now, if you want to multiply this all out and combine it and get some cubic, some degree 3 polynomial, and then try factoring that, go ahead. Nothing wrong with that. But I'm seeing this. Okay, so we have 1 minus lambda, and then lambda squared minus 2 lambda minus 3. That factors this way. It's lambda minus 3 multiplied by lambda minus 1. Okay. Then we have negative 2. Now, the 2 lambda minus 6, I can pull a 2 out of this, making this -4, right? 2 times 2. And if I pull a 2 out of this factor, I get lambda minus 3. And then here, I have -2. If in this last factor, this factor of this last term, -6 lambda plus 18, if I pull out a -6, if I factor out -6 from these two terms, I'll have -2 times -6, I'll have positive 12 on the outside. And then I'll have lambda minus 3, right? Because -6 times -3 is positive 18. Now look at all three of these terms. Lambda minus 3 is a factor of the first product. Lambda minus 3 is a factor of the second product. Lambda minus 3 is a factor of the third product. They all have a common factor of lambda minus 3. So I can pull lambda minus 3 out of all of them. And once I do that, what's left over is, if I pull lambda, it's 1 minus lambda times lambda minus 1. And then minus 4 plus 12, so plus 8. Right? Because again, the lambda minus 3 is gone, so that's plus 8. And then I simplify what's in the brackets here. So lambda minus 3 multiplied by, negative lambda squared. And then, we have a plus lambda plus another lambda, so plus 2 lambda. Right? And then minus 1 plus 8. Minus 1 plus 8 be plus 7. Okay, and then if you like, and oh, okay. Sorry, I moved the paper on you because I noticed a mistake while I was writing this. When I got down to here, I was like, oh, that's not very pretty. My mistake was up here. I'm sorry if you've been writing with me so far. When I factored lambda squared minus 2, and that's lambda minus 3 times lambda plus 1. So then when I pull out the lambda minus 3's, I get lambda minus 3 times, and then in the brackets here, 1 minus lambda times lambda plus 1, and then plus 8. So my apologies, this line I'm going to erase, alright, skip over, let's move down here. So sorry. And now we have, alright, again, the factor lambda minus 3, and then this in the bracket, got, negative lambda squared, and then you have minus lambda plus lambda, so no lambda to the first. And then plus 1 plus 8, that's plus 9. Which, very often you've probably seen in algebra text, they don't like negative leads on polynomials. So if I factor a -1 out of this factor, I'll have -1 times, I'll pull that out front here, times lambda minus 3, I still have that factor going. And then if I pull -1 out of this, it's lambda squared minus 9 that's left over. And that's a difference of squares. So I get, now -1, you can just write a minus sign, that represents -1, times the factor lambda minus 3. And then lambda squared minus 9 factors to lambda minus 3 times lambda plus 3. Alright, a difference of squares. And I'm seeing the same factor twice here. So we have -1 times, and then lambda minus 3 squared times lambda plus 3. All right. So again, sorry about my little snafu. See how important signs are. Pay attention to your signs. That's a big lesson to learn from this mistake. And now that I have, this is a degree 3 polynomial here completely factored, and we're trying to figure out, where is this determinant, where is this characteristic polynomial, right, equal to 0. So this equals 0 when, lambda minus 3, one of the factors is 0, so when lambda equals 3, or when lambda plus 3 is 0, and that would be when lambda equals -3. Alright, so I have the spectrum for matrix A now, right, the set of all the eigenvalues. Alright, so the spectrum of A is just the set with -3 and 3 in it. Alright, those are the only two eigenvalues. And now that we've solved this characteristic equation, we can also see the algebraic multiplicities of the eigenvalues. Alright, so look at 3. 3 has, two factors in this characteristic polynomial that it makes 0, right? There's lambda minus 3 twice, right? Look at the power. So the algebraic multiplicity of 3 is 2. Right? There are two factors that 3 makes equal 0. There are, the 3 is a repeated solution twice, right? And then looking at -3, right? -3 doesn't make that factor 0, but it makes, lambda plus 3 equals 0. And there's only one of those, right? If there's no exponent, there's an exponent of 1. So the algebraic multiplicity of -3 the algebraic multiplicity of -3 is 1. Right. Wonderful. Oops, sorry, making a lot of noise there, dropping markers all over the place. Okay, so we found the spectrum, found the stated the algebraic multiplicities of the eigenvalues. So now we can go in and find, this is where I'm going to probably go to the calculator, help us out finding the eigenspaces corresponding to these eigenvalues. All right, so back here was the matrix. All right, here was matrix A, that 3 by 3. So now we're going to find the eigenspaces. All right, so the first eigenspace I'm going to do for 3, all right, for lambda equals 3. I'm going to find the eigenspace of A corresponding to lambda equals 3. Right. So remember, that involves solving this equation, right? Finding all the solutions of A minus lambda I, so 3I, multiplied by some vector x. When's that equal to the 0 vector? Alright, I'll write out the matrix. What is this A minus 3I? Let's just, take matrix A and subtract 3 from all the diagonal entries. Right? So 1 minus 3, -2, 5 minus 3, +2, -3 minus 3, -6, and then all the other, non-main diagonal entries stay the same. So 2, -2, -2, -2, -6, 6. All right. And then multiply by, the vector x here would have to have 3 components, so say x1, x2, x3. And we wish this to be equal to the 3 by 1 0 vector, right? The 0 vector from R3. All right, and as with the examples before, right, I wish to take this matrix, put it into reduced row echelon form. Alright, now this one again is not too terrible, because look, the first row is the same as the second row, and the first row times 3 would give me the third row. So if I took the opposite of the first row, added it to the second row would be all zeros. And if I took -3 times the first row, added it to the third row, and get a new third row, the third row would be all zeros. And then to get it into reduced echelon form, get that leading non-zero entry in the first row to be a 1, I would multiply everything in the top row by negative 1/2, right? So again, you can go to a calculator, but this shouldn't be too bad, right? So I'd have, if I multiply, I'd get 0 rows for the second row and third row. And top row 1, negative 1, 1, right? Multiplying the top row by negative 1/2. And again, imagine there's an equals, this equals 0 stuff on the other side. Looking for my pivots. The only pivot here, the only one of those leading ones is in the first column. So the variable x1 is basic. And the other two variables, right? The other two columns do not contain a pivot. So x2 and x3 are free variables. And there's two different variables, so I'm going to let each one be represented by a different parameter. Say x2 as the value of s, where s is any real number. And say x3 has the value of t, where t is any real number. And then from the first row here, we're seeing that x1, minus s, right, I called x2 s, plus t, called x3 t, x1 minus s plus t must be equal to 0. And solving for x1, I would add s and subtract t. So x1 must be equal to s minus t, right? Whatever my choice of s is and whatever my choice of t is. So putting this all together, we get our solutions. I can replace the vector x there with anything that looks like this. Right, it's going to have 3 components, where the first one is, s minus t, whatever I choose for s minus whatever I choose for t. The second component is just whatever I choose for s. Third component is whatever I choose for t. And then, as in the problem earlier, right, there are 2 free variables. I can separate these, and I'm just going to pull the variables out right now. So one involving s, so I have s times and then the vector with the coefficients of s, 1, 1, 0. And then I would add to that a vector involving the other free variable t. And pulling that out, I get a vector with the coefficients of t, negative 1, 0, 1. Alright, so what we're seeing here is that every solution to this equation, right, this a minus 3i times x equals 0, is a linear combination of the vectors 1, 1, 0 and negative 1, 0, 1. And there's my eigenspace, right? All the eigenvectors of corresponding to 3 along with the 0 vector, right? Because again, the 0 vector is a solution to any of these. So the eigenspace of A corresponding to 3 is, again, you can write the linear combinations as long as s and t are real here, or just remember what the span is, right? This is the span of the set with the vectors 1, 1, 0 and negative 1, 0, 1. There's the eigenspace of A corresponding to 3. This set with the 2 vectors that I have here are linearly independent and clearly span the space, so they are a basis for it, therefore an eigenbasis. Right, just this set with the vectors 1, 1, 0 and the vector negative 1, 0, 1. And we're seeing now that the dimension of this space, this eigenspace corresponding to 3, is 2. Right? There are 2 vectors in an eigenbasis, and that's also called the geometric multiplicity of lambda equals 3. So the dimension of this eigenspace of A corresponding to 3 is 2, which again is called the geometric multiplicity. for that particular eigenvalue for lambda equals 3. And just double check the statement, is the it should be true that the geometric multiplicity of an eigenvalue is less than or equal to the algebraic multiplicity. And we saw that earlier. Where did I throw that? Oh, here it is. So there, so we saw the algebraic multiplicity of 3 was also 2. Right? So that in this case they're equal. Right? But again, one more time, geometric will be less than or equal to algebraic. Okay, so that was for 3. Right? That was the eigenspace and eigenbasis and geometric multiplicity corresponding to lambda equals 3. Now I'm going to do -3, and that'll be it. Right? That's the last eigenvalue for this particular matrix. I guess this is part 3. Right, let's find the eigenspace of A corresponding to -3. Right, so remember how this goes. It's the same stuff. Trying to solve this equation. A minus -3i, so A plus 3i, times some vector x. When's that equal to the 0 vector? Now, what is this matrix? What is A plus 3i? It's just matrix A, where I'm adding 3 to the main diagonal entries. So 1 plus 3, 4. 5 plus 3, 8. -3 plus 3, 0. And then all the other entries remain the same. And my vector x is again going to have 3 components, so let's say x1, x2, and x3. And I wish this to be equal to the 0 vector from R3. 0, 0, 0. Alright, so I don't feel like bothering with this one. This one isn't as particularly nice as the last one. So this time I'm going to go to the calculator. Now you could do it by hand, right? Do row operations until you get this into an echelon form, whether it be a row echelon form or reduced row echelon form. I prefer reduced row echelon form, so I'm going to go to my calculator here. I got my 84 plus, similar to the 83 if you got it. I've already got a 3 by 3 entered here, so let me just change the entries. So we have 4, 2, -2, -2, 8, -2, -6, 6, and 0. Just double checking those real quick. Looks good. Then the last thing I entered was actually reduced row echelon form. So again, if you go back to the matrix and then over to the math menu, you should scroll until you see RREF and then put matrix A in there. Okay. And this is -1/3 and -1/3, 0.3 forever. I'm not going to change that to fractions. I know what those are. Alright, so here we are. This matrix in reduced echelon form. 1, 0, 0, 0, 1, 0. And then -1/3. Looks like -1/3 again, and then 0, right? You should have at least one row of zeros with these. Okay, looking at the pivots, right? There's a leading one in this column, a leading one in this column. So x1 and x2 are basic. The third column, right, does not have one of those pivots, so x3 is free. Now notice the fractions. Normally I let x3 be like s or t, but when there are fractions involved as my coefficients, I'm going to replace x3 with an expression that would get rid of those denominators. So what's the least common denominator of these two fractions? That would be 3. So instead of letting x3 be t, I'm going to let x3 be 3t. So when I replace x3 with 3t, these denominators are canceled. Alright, so then from the first row, we see that x1, x1 minus a third of x3. So a third of 3t would be t. So that's x1 minus t equals 0. Adding t to both sides, we get x1 equals t. Same thing here. We're seeing x2, right? 1x2, again minus a third of x3, or minus a third of 3t, or minus t, would be equal to 0. And then adding t to both sides gives me x2 equals t as well, right? Whatever my choice of t is. So putting all these together, we're seeing all the solutions. Now this time I'm just going to pull the t out. Right? I can replace all the solutions to this equation. I can replace x with any vector that looks like this. There's only one free variable. I pull it out. T times the vector 1, 1, 3, right? x1, x2, x3, the coefficients of t, 1, 1, 3. And there we go, right? Every solution of this equation is some scalar multiple of the vector 1, 1, 3. Another way to put that is that the eigenspace of A corresponding to -3 is the span of the set with just the vector 1, 1, 3 in it. So this does include the 0 vector, but any non-zero vector in here, remember, it would be an eigenvector corresponding to -3. So there's the eigenspace, and then we can very hopefully clearly see an eigenbasis for this space. Which is just this set with the vector 1, 1, 3 in it. And looking at that, the dimension of this eigenspace, right, the dimension of this eigenspace of A corresponding to -3 is just 1, right? There's only one vector in a basis. And recall that the dimension of an eigenspace was called the geometric multiplicity. For that particular eigenvalue of lambda equals -3. All right. And just to be sure, all right, remember that statement earlier, the geometric multiplicity of an eigenvalue should be less than or equal to the algebraic multiplicity. Well, this was earlier. Remember, the algebraic multiplicity of -3 was also 1. Right? So it's equal this time. I only saw one example so far in this video where it was less than. But just know that that can happen, right? The geometric multiplicity will either be less than or equal to the algebraic multiplicity of an eigenvalue. Great. All right, lots of stuff going on there. All right, so when given a square matrix, if you're asked to find the spectrum, right, the eigenvalues, you find the solutions to that characteristic equation, that determinant of A minus lambda I equals 0. Once you find those solutions, then say how many times do these solutions repeat in the equation. The number of times a solution repeats in the equation, the characteristic equation, that'll be the algebraic multiplicity of that eigenvalue. Okay. Then you take an eigenvalue, lambda, and then you go and solve A minus lambda I times x equals the 0 vector. Find the values of x, the vectors x that make that true, and all of those solutions make up the eigenspace of A corresponding to lambda. And if you've found those solutions in a proper way using reduced echelon form or an echelon form, you should very easily be able to spot a basis for the eigenspace, right, or an eigenbasis. And then once you have an eigenbasis down, just how many vectors are in that eigenbasis, right? That'll be the dimension of the eigenspace, and that dimension of the eigenspace corresponding to lambda is called the geometric multiplicity of lambda, right? And that should be less than or equal to the algebraic multiplicity. So lots of stuff going on there. So I hope you found these examples useful, and hope you enjoy practicing some on your own. And thank you very much.